So this is the Scholarship Statistics Exam 2013, and we're going to be doing question 3b. If you want to see a video going over question 3a, there's one of those too. You can find it on YouTube. So question 3b. Ice cream tubs are required to have a weight between 500 grams and 520 grams in order to be considered acceptable. As part of a quality control process, a large random sample of tubs was taken which had a mean of 513 grams with a standard deviation of 3.5 grams. So when we get given a parameter or statistic, we should always write it down as we go. So mean x bar of 513 grams and standard deviation S of 3.5 grams. Now, you might be wondering, why did I use X bar and S rather than what you'd normally see, which is mu, the Greek letter, and sigma? Well, the reason is we use mu and sigma, the Greek symbols, when we're dealing with population parameters, so known numerical characteristics of a population. And so, as we know, for the mean, that's the Greek letter for M, which is mu, and for standard deviation, it's the Greek letter for S, lowercase s, which is sigma. When we're dealing with sample statistics, because here it's only from a sample, we need to communicate that as statisticians, and we communicate that by using different symbols, and we tend to use English letters when we're dealing with sample statistics. So for the mean, we use X with a wee bar on top, and for the sample standard deviation, we just use the English letter S. So it's just to communicate that we're dealing with only a sample. And that's really important, isn't it? Why is that important? Well, it's important because with a sample, we only have some information. We don't have all the information about the population. And we need to remember that. So there's always going to be that element of uncertainty, isn't there, when you're only dealing with a sample. So giving a different symbol communicates that uncertainty to the reader. Okay, so continuing with the problem, what are we being asked to do? Assuming a normal distribution model, so we're told normal distribution, determine whether current production is meeting acceptable requirements. Then it says justify your answer. Always underline any verbs. Verbs are really important because often we know there'll be marks for each one. For example, here, easy mistake to make is to solve the problem and then forget to justify your answer, then you wouldn't get full marks. So take your time. Okay, so to get started, since we know what distribution it is, we know which distribution it is, we need to start by sketching that distribution. So let's sketch a normal curve. So here's our normal distribution curve. So we start by marking in the mean, X bar, and it was 513 grams. So sample mean. Next thing we do is we mark in our standard deviation, and what I always encourage students to do, the way to remember it is slice and dice. Slice and dice. And the S and the D remind us standard deviation. And we know with a normal curve that almost the entire data, so 99.7%, lies within 3 standard deviations either side of the mean. So let's mark in, so let's slice and dice it, and because it's plus or minus 3, that means we've got a total of 6 slices. And we mark in our standard deviation. Sample standard deviation was 3.5 grams. Next, we return back to the question again and just check what we're being asked to find out. So acceptable weights are those between 500 grams and 520 grams. So unacceptable would be outside of that. And we're being asked to determine whether the current production is meeting acceptable requirements. So this data from the sample, notice we're not given a sample size at all. So that means that without a sample size, we can't be expected to do anything like a confidence interval. We haven't got access to any technology. We actually don't have the data set. So obviously, we're not being asked to take sample size into account here. So we're simply being asked, based on this data, all we know is the mean and the standard deviation. So based on that, how likely would it be to get an ice cream container that breaches these requirements? So that's outside of the 500 grams, 520 grams. So where should we start? Well, the easiest place to start is to work out the probability of getting an ice cream container that meets requirements. So that meets requirements. And how do we do that? Well, we need to work out what percentage of them would be expected to meet the requirements. So to be between the lower limit of 500 grams and the upper limit of 520 grams. Always write the limits in first, and then our x value, x is in the middle, and we want x to be bigger than, or heavier than 500 grams and lighter than 520 grams. Don't need to worry about putting a line underneath, because with normal distribution you can be infinitely precise because it's a continuous variable. So greater than and less than is fine. Always check that the signs are pointing the same way. So now we need to actually show this on our diagram. So 500 grams, how far below the mean is that? We know each standard deviation is 3.5 grams. So that's a difference. How many standard deviations? It means we're right in near the left. So 513 minus 2 standard deviations would take us, that'd be minus 7, so that'd be down to 506. Another standard deviation, 502.5, so we're actually more than 3 standard deviations below the mean. So we're squished right into this bottom bit. Okay. What about at the other end? Well, 520 grams, how far above the mean is that? Well, 513 plus a standard deviation, that'd be 516.5, and then plus another standard deviation, 520, so we're 2 standard deviations above the mean here. So that's 520. So we want to work out the bit in the middle, the gap in the middle. Okay, so the probability it meets requirements, let's grab our graphics calculator. We need the probability that x is between 500 grams and 520 grams, based on a mean of 513 and a standard deviation of 3.5. So menu distribution, well, menu stat distribution normal, NCD, and so our lower is our 500 grams, our upper is our 520, our standard deviation is 3.5, and execute, and we get 0.9771497. So let's write that down. So what does that mean? Well, it means that about 98% of ice cream tubs that are produced fall within the requirements. So they satisfy the requirements. Based on, what are we assuming here? Well, we're assuming that this normal distribution model is a good fit. So based on this normal distribution model. So what else are we assuming here? Well, we're also thinking, where did this data come from? Well, it only came from a sample, so this is from a sample only, and we should acknowledge that. Doesn't mean that it's not valid. In fact, most data in the real world is from samples. Very hard to collect data on an entire population. Think of trying to get the data from all the ice cream that comes off this particular manufacturer, off their production line. What even would the population be? I suppose we're looking at ice cream that they produce in general, aren't we? So there's no way that you could ever obtain information on all the ice cream they've ever produced with their current process. So a sample is essential, isn't it? That's all we're going to get in this situation. So we should acknowledge this is from a sample. So how do we say that? What are we assuming? Well, we're assuming that the sample is representative of the population of all ice cream tubs produced by this manufacturer. Okay, so we've acknowledged the assumptions that we're making and the source of the data. Now, let's check if we've answered the question yet or not. So, assuming a normal distribution model, we've done that. Determine whether the current production is meeting acceptable requirements. So what do they mean by that word acceptable? Well, what do you think? What do you reckon that we should say here? So, what were our findings? Our findings were that about 98% of them are meeting the requirements. Is that acceptable? Well, you could actually argue either here and they would give you the marks. So let's actually have a wee look at the marking schedule and see what they said. So if you go to the NZQA website and under Mathematics and Statistics Scholarship, you can download the assessment schedule, and here it is. It says general principles: ignore incorrect answers alongside correct answers. The exception is contradictory statements. Ignore minor copying errors. So we're going down to question 3b. So here we go, 3b. Okay, evidence. Let x equal weight of an ice cream tub. And they've calculated, what have they calculated? They've calculated the probability of x being between 500 grams and 520, which is what we did. And they got about the same thing as us, 0.9771. They've said assuming a normal model, which is what we talked about. And then they've made the same sort of conclusion of 97.71% of current production is within acceptable limits, thus meeting acceptable requirements. So they've said that makes it acceptable requirements. Note, and it's got a couple of things that they let you do, mistakes they accepted. You could also work with a complement. So obviously if you subtract the 97.71%, if you subtract that from 100%, and that gives you the probability of a tub going outside the acceptable requirements. And out of spec can be calculated instead, leading to an unacceptable argument of 2.29% being outside the specified limit. Doesn't say why that's unacceptable. Continuity correction incorrect. Well, that's because we're dealing with continuous data, so you only need to make a continuity correction if you're using the normal distribution to model discrete data, or if you're using any continuous distribution to model discrete data. But this is not discrete, it's weight, so it's continuous. So score partial, P for partial, is reference is made to a confidence, or if reference is made to a confidence interval. Confidence intervals not really that relevant here, are they? So we don't have the sample size, which you need for a confidence interval. Okay, judgment. S for scholarship. Scholarship level, correct answer with an appropriate method. P, some indication of correct method. This is a pretty easy scholarship question, really. In fact, it'd be an easy excellence question in NCEA. One of the things you could look at here that they could ask is they could have given you a question where this percentage was lower, and then asked you ways to improve this process. And so if the percentage had been quite low, and how would you improve the process? If they did ask you that, and you could get one like that this year, one of the things I notice here, so we're just sort of talking hypothetically now, notice how the proportion too heavy is much higher than the proportion too light. So what does that suggest? Well, it suggests that based on the sample, there's a greater risk of getting an ice cream tub that's too heavy than too light. So one of the ways to improve the success rate so that more of them meet the requirements could simply be to reduce the mean. In other words, to actually keep the specifications the same, but set the equipment to produce slightly lighter tubs. In other words, dispense slightly less ice cream per tub. So that would then shift this distribution down, wouldn't it, to the left? And so, you know, for an extension idea, if you're going for outstanding scholarship grade, you could investigate the effects of that. So if you shifted it, say, to so that the Z scores at the 500 and the Z score at the 520 were the same, what would the mean have to be reduced to? And then would that reduce the percentage that fall outside of specifications? So that would be, if you're really going for an outstanding scholarship this year, that's a good extension to this question. So find the mean that would ensure a Z score the same for the upper limit as for the lower limit. So that the same percentage are too heavy as the percentage that are too light. And find out the effect that has on the resulting percentage that meet requirements. Thanks for listening.